So I want to get started here a little bit into section 6.8. Again, just trying to make up a little bit for our freeze days that we had here so we can keep on track. We're looking at our first exam for next Thursday, a week from today. So in this last section of the chapter, we're going to look at things called indeterminate forms and L'Hôpital's rule. Now this is French. It looks like La Hospital, but it's not. The S is silent and the last syllable is accented. It's L'Hôpital. So in this first example here, I want to look back at a limit from Calc 1. And we're looking at the limit as x approaches negative 1, x squared plus 3x plus 2 over 2x minus 2. And we're going to look at the traditional way we would do this limit. First, we would look and see if we can plug in negative 1, because this is a continuous function as long as negative 1 is not a 0 for the denominator. But if you plug that in the denominator, you'd get 2 times negative 1 is negative 2 plus 2. That's 0 in the denominator. And if you plug it in the numerator, you get 1, negative 1 squared, plus 3 times negative 1 is negative 3, so we get 1 minus 3 is negative 2 plus 2 is 0. So this is actually a form 0 over 0. And remember in Calc 1, when you had a limit that was 0 over 0, you had to do some more work. And the more work was usually to factor. So we're going to write this as limit x goes to negative 1. And in the numerator, we are going to FOIL backwards. So factors of 2 that add up to 3, that's going to be plus 2 and plus 1. And then in the denominator, we've got a common 2 that we can factor out. And what will be left is x plus 1. And then we can cancel these factors of x plus 1. So now we are left with x plus 2 over 2. And we are still taking a limit of that. X plus 2 over 2. So these two expressions are equal every place except at x equals negative 1. And since x is approaching negative 1 and never reaches negative 1, the two limits will still be equal. But this limit, this is a continuous function at negative 1. We can just plug in to get that limit. It's negative 1 plus 2 over 2. So that's 1/2. Okay, so this is all well and good, but I want to show you a different way that we could calculate this limit, and when you run into more complex limits, you can do this same procedure. So, and this is for things that are form 0 over 0. That's called an indeterminate form, because we can't determine what's going to go on without some more work. And here the more work was we had to factor and remove common factors. Well, let's look at this same limit. I brought it down here. But now let's take the derivative of the top and the bottom separately and see what that limit looks like. So this is not a quotient rule. I'm just doing derivative top, derivative bottom. So the derivative of the top there, keep my limit out in front here. X approaches negative 1. So derivative x squared is 2x. Derivative 3x is 3. And then downstairs, derivative 2x is 2. And derivative 2 is 0. And as x approaches negative 1, this limit, this function is continuous. So to compute that limit, we can plug in. So 2 times negative 1 is negative 2, plus 3 is 1. This is 1/2. And oh look, 1/2, 1/2. And that was not by accident. So this idea of differentiating the top and the bottom separately and getting this new function, which hopefully is easier, that's the idea of L'Hôpital's rule. Okay, but it's only if you have an indeterminate form, in this case 0 over 0. So you always have to check this first, because you can't apply L'Hôpital's rule unless you have an indeterminate form. You can't do it with determinate forms. So for example, if we wanted to look at limit as x approaches 0, 1 minus e to the x over sine x. So as x goes to 0, e to the x approaches 1, and sine x approaches 0. So this thing is looking like 1 minus 1 over sine of 0. That's 0 over 0. That's indeterminate. We don't know what's going to happen there. Okay, we'd have to do some more work. So both top and bottom are approaching 0. It depends on who gets there first. You could end up anywhere from 0 to infinity or someplace in between. So this kind of thing, we really can't do it without L'Hopital's rule. But here I wanted to show you with one that we did have a different method to compute that you really get the same thing. So here's what L'Hopital's rule says. It says for limits that have the form 0 over 0 or infinity over infinity, so those are two indeterminate forms, you can't tell what's going to happen unless you do more work. In those cases, the limit as x approaches a of f of x over g of x will be the same as the limit of f prime over g prime as x approaches a if that right hand side exists. And exists plus infinity and minus infinity are okay to have that limit exist. We also need here that g of x is not equal to 0. It can approach 0, but it can't equal 0. And then x approaches a, that'll work if you have a limit x approaches a from the plus side or from the minus side, or if x is approaching plus or minus infinity. So lots of different versions of L'Hopital's rule. Now just a warning here, okay, you want to compute f prime over g prime, not the quotient rule. Okay, we're not taking derivatives, we're just doing derivative of the top, derivative of the bottom separate. That's L'Hopital's rule. It's not the quotient rule. So let's put this to work here. Compute a few limits. So limit as x approaches infinity, 3x cubed plus x over x cubed minus 1. So as x approaches infinity, x cubed here approaches infinity, and so does x, so the top's going to infinity. And then the bottom, this x cubed approaches infinity, subtract 1, that's still going to infinity. This is form infinity over infinity. So there we checked that it was an indeterminate form, right? It's only these two guys where L'Hopital applies. 0 over 0 or infinity over infinity. And minus infinity over minus infinity, that's okay. Or minus infinity over plus infinity, that's okay. It's just the difference of a minus sign. So since this is an indeterminate form, we can apply L'Hopital's rule. So this will equal the limit as x goes to infinity, and then differentiate top and bottom separate. So derivative of the top is going to be 9x squared plus 1. And then the derivative on the bottom there is 3x squared. And then derivative of 1 is 0. So now what's going on? Well, as x goes to infinity, this 9x squared goes to infinity, plus 1, that goes to infinity, and then the 3x squared, that also goes to infinity. This is still infinity over infinity. We still can't tell what's going on. But we can apply L'Hopital's rule again. Oh, I forgot. When I use L'Hopital's rule here, I put an L above the equal sign, as well as putting the indeterminate form underneath. And if you would do that for me both, put the L there to tell me, hey, prof, I'm using L'Hopital's rule on this limit, not doing something else. And then put the indeterminate form underneath to tell me, hey, I really checked that it's going to work. So I'm going to use L'Hopital's rule again. So you can do it again. You can do it as many times as you need to, as long as the last limit exists. So this will now be limit x goes to infinity. Now we'll differentiate again. Derivative of the top, this will be 18x. Derivative 1 is 0. Derivative 3x squared is 9x. And now the x's cancel, right? Pew, pew. Had to do that for my wife. And then 18 divided by 9 is 2. This is just the limit of 2 as x goes to infinity. And that's 2. Okay, it always stays as 2. Okay, so that's L'Hopital's rule. Now, in Calc 1, we had another way to do these limits. We would look at dominant terms, right? The highest powered terms, determine what's going on. That's for limits as x goes to infinity or negative infinity. So we could say, well, by dominant terms, and I'd usually put dt above to tell dominant terms. By dominant terms, this is the limit of 3x cubed over x cubed, and then the x cubes cancel, right? And we get, oh, x is going to infinity. And we get 3. Oh, you know what? We got 2 up here. We got 3 down here. What happened? What happened was I wasn't paying attention here. 2 times 3 is 6x, not 9x. That should be a 6. 6 right there. 18 divided by 6 is 3, not 2. Now we got the same thing. Limit of 3 is 3. So notice 3, 3. So whether we use dominant terms or L'Hopital's rule, we got the same thing. So again, I did this example for a problem that we had another method to do, and you might say, well, yeah, this is easier here. And yeah, it is on this problem, okay? But now here we're back to the one we're looking at up here. We have no other way to do this problem. We got to do L'Hopital's. So we know that this is 0 over 0. We already checked that. So we're going to use L'Hopital. And derivative of 1 is 0. And derivative of negative e to the x is negative e to the x. So this will be limit x approaches 0. Derivative 1 is 0. Derivative of negative e to the x is negative e to the x. And then in the denominator, derivative of sine x is cosine x. And now can we do the limit? Well, x approaches 0, e to the x approaches 1, so now this looks like negative 1 on top. And then on the bottom, cosine of 0 is 1. Okay, so that's a continuous function. We can plug in to get the limit. This is just negative 1. So we only needed one application of L'Hopital's rule, and we got that limit. There was no other way to do that without L'Hopital. Okay, so I showed you a couple examples where where there's another way to do it, just so we could see that, hey, this is really giving us the right answer. And now here's one we couldn't do without L'Hopital. Let's look at one more here. Limit x goes to infinity, 4x cubed over e to the 3x. Okay, we got no other way to do this except L'Hopital. But remember when we talked about the relative growth rate of functions, we've got a power function on top, and we got an exponential function on the bottom. X is going to infinity, so this x cubed is going to go to infinity. And then e to the 3x, remember that looks like this. Goes up from left to right. As x goes out to infinity, that bugger takes off and goes to infinity. So they're both infinity. So it's an indeterminate form, so we can use L'Hopital. But notice here, we got a power function on the bottom, on the top, and an exponential on the bottom. And remember that exponentials grow a lot faster. So that 4x cubed is much less than e to the 3x. So when we do a ratio like that and have that exponential on the bottom, that's growing a lot faster. So the bottom of the fraction's getting bigger. That makes the fraction smaller. This thing should go to 0. Well, let's check it out and see. So this will be limit x goes to infinity. And the numerator, 3 times 4, 12, 12x squared. And in the denominator, e to the 3x times 3, if we do our derivative. So 3 e to the 3x. Okay, well, and our power went down in the numerator, but this is still form infinity over infinity. So we got to do L'Hopital again. So limit x goes to infinity. Another derivative. 2 times 12 is 24x. And in the denominator, we're going to get another factor of 3, e to the 3x times 3. So this will now be 9 e to the 3x. And as x goes to infinity, top and bottom still going to infinity. It's still an indeterminate form. So we got to do L'Hopital one more time. And we differentiate top and bottom one last time. So limit x goes to infinity. Derivative 24x is 24. And we get another factor of 3 in the bottom. This will now be 27 e to the 3x, because it's e to the 3x times 3. So now the top is a number and the bottom is going to infinity. So now this is number over infinity. Okay, fixed number on the top, bottom's getting bigger and bigger, ratio goes to 0. And that's what we expected here, because the bottom is much bigger than the top. So as long as this last limit exists, you can do L'Hopital, go back and do L'Hopital as many times as you want to. Now if you get to this last limit, it does not exist, can't use L'Hopital. Happens once in a while. So those are basic limits for L'Hopital and basic indeterminate forms. Now sometimes you run into an indeterminate form that looks like 0 times infinity. So one piece is going to 0, the other piece is going to infinity. And when you deal with that, you just want to change it to either 0 over 0 or infinity over infinity. So let me show you what I mean. So here we want to do limit x goes to infinity, 3 to the negative 2x, x squared. Okay, so 3 to a negative power. Remember that 3 to the negative 2x, that's going to go down from left to right. So as x goes to infinity, this piece here is approaching 0. And then that x squared is approaching infinity. So this is 0 times infinity. So what we want to do is take that negative exponent, bring it down on the bottom as a positive. So this is just doing algebra. Limit x goes to infinity, x squared on the top, and now 3 to the positive 2x on the bottom. So now top's going to infinity, and 3 to the 2x, that goes up from left to right. And as x goes to infinity, that guy's going to go up to infinity. So this is infinity over infinity. We can use L'Hopital now. So now differentiate top and bottom separately. So derivative x squared is 2x. And then the derivative on the bottom, derivative of 3 to the 2x is 3 to the 2x times the derivative of the inside function, 2, times log of the base, because it's not e, so ln of 3. So what now? Well, x is going to infinity, 2x goes to infinity. And then the 3 to the 2x on the bottom times the number, still going to infinity. This is still infinity over infinity. We got to do L'Hopital one more time. And let's see here, limit x goes to infinity. And now derivative 2x is 2. And then the derivative of 3 to the 2x is 3 to the 2x times 2. And then times log of the base, ln 3. And then we've got another 2 and another log 3 from the previous step. So this will actually be 2 squared and natural log of 3 squared. Got 2 factors of those, 1 for each derivative. Well, this 2 here can cancel one of those 2's off, so we're left with a 1 on top. Oh, sorry, forgot to make sound. Pew, pew. Okay, so now what? Got a number on the top, 3 to the 2x on the bottom. This now looks like number over infinity as x gets bigger and bigger. Top of the fraction's fixed, bottom is getting bigger and bigger. That ratio goes to 0. So we're done. And we would expect this looking here, right? Because a power function and then an exponential function. Remember that that power function is much smaller, much less than that exponential function. Or the exponential function is much bigger than the power, it grows faster. So the bigger thing's on the bottom, that's going to make the ratio go to 0. Okay, didn't have any other way to do that one except for L'Hopital. So this is intuition here, okay, to say which one's growing faster, but you have to carry out L'Hopital. You actually have to compute to make sure that your intuition's correct. Because sometimes your intuition, you think, oh, I think it's going to do this, and then you compute it, and it doesn't. So you really have to go through the computations there. Okay, one last example, and we'll call this good enough until till tomorrow. We want limit as x approaches 0 from the plus, x times ln of x quantity squared. So this piece, the x, that's approaching 0. And then remember, natural log of x, that guy looks like this. Okay, and as x approaches 0 from the plus side, that goes down to minus infinity. So this inside's approaching minus infinity. It gets squared. This whole thing, that's approaching infinity. So 0 times infinity, okay? We got to change it to 0 over 0 or infinity over infinity. So we got to bring one of these things down to the bottom as a negative exponent. It's going to be easier to bring that x down than the natural log. That'll be kind of messy. So let's do that. So this will be limit x approaches 0 from the plus. And we are going to leave our natural log of x squared on top. And then on the bottom, x to the negative 1, which is 1 over x. So as x approaches 0, this bottom goes to infinity, top goes to infinity. This is now infinity over infinity. That's an indeterminate form. We can use L'Hopital. Now, with the log function, this is an outside exponent. That will not factor down in front. It's only inside exponents. So can't use properties of logs there. So now we start taking our derivative of the top and bottom separate. So this would be limit x goes to 0 plus. This is a function to a power. So exponent comes down in front, times the function ln x, decrease your exponent, so now it's first power, and then times the derivative of the inside. So times 1 over x is the derivative of log x. And then on the bottom, x to the negative 1, that derivative is negative x to the negative 2. Negative 1x to the negative 2. And now let's simplify this thing before we decide, whether we're done, whether we have to do L'Hopital again. So this will be limit x approaches 0 from the plus. And then this on the bottom, that negative x to the negative 2, that's the same as negative 1 over x squared, right? Because a negative exponent means reciprocal. So negative 1 over x squared dividing by negative 1 over x squared means multiply by the reciprocal. So we've got this 2 ln x times 1 over x, and then times the reciprocal at the bottom, which would be negative x squared over 1. Okay, so this x will cancel one of those. Okay, and what do we got left here? So we've got a limit x approaches 0 from the plus side. We got a 2 ln, ln x. And then we've got negative x on top. Let me put the negative out in front, and then times x. So what does this look like? Well, as x approaches 0, this piece approaches 0, right? And then negative log of x, that goes to minus infinity, multiplied by negative 2. This piece approaches infinity. Okay, so 0 times infinity. Oh, that's what we had to start with. And what did we do there? We brought the x down. Okay, so let's do that again. So we're going to have to do L'Hopital one more time. So limit x approaches 0 from the plus. Negative 2 natural log of x. And then divide by x comes down, x to the negative 1. So now this is infinity. This is approaching infinity. That is infinity over infinity. That's now an indeterminate form. So we can do L'Hopital. Okay. So limit x approaches 0 plus. And derivative of natural log is 1 over x. So this will be negative 2 times 1 over x. And then the derivative on the bottom is going to be negative 1 comes down, x to the negative 2. Negative over negative, we can change that to a positive. And then got to do some algebra here. So this is going to be limit x approaches 0 from the plus side. And we've got that 2 times 1 over x. And then x to the negative 2 is the same as 1 over x squared. And dividing by 1 over x squared is the same as multiplying by x squared over 1. So this will be limit x approaches 0 from the plus side, 2 times 1 over x, and now multiply by x squared over 1, invert and multiply. And oh look, x's will cancel. Okay, and they're gone. They're out of here, destroyed. They went home and got some hot chocolate, a tall cup, and they're keeping warm. So now limit x approaches 0 plus. We've got a 2 left, got an x left. That's it. And that's no longer an indeterminate form. X goes to 0, 2x is going to approach 0. Oh, we got it. Okay. So that approaches 0. So let's look at our intuition here. So we've got a log function that's going to infinity, and then we've got x, which is going to 0. And you look at this log function, it goes down to minus infinity really fast, and you'd think that if you squared that, that's going to go up to positive infinity really fast, and you would think that that would win out over x, right? Because the y equal x just looks like that, and if x is approaching 0 from the plus side, it's just coming down to 0 linear. It seems like this log's going to win out, but didn't turn out that way. The x won out. So got to be a little bit careful there. All right, let's call that good enough. We'll do more examples when we get back in class. So if you would please, for Friday, try homework problems from section 6.7, please.